Hey, so welcome back, and this is another daily LeetCode problem. So today it was called Number of Closed Islands, and it's a graph algorithm. So you're given this 2D matrix here, and you want to figure out how many closed islands there are. And so here there's two of them, and that's because they're all surrounded. These zeros represent land, and the ones represent the water. And you see that they're totally surrounded at every kind of edge by water. It's also okay in this case where you can have kind of a donut shaped island where you have like water in the middle of it. Okay, and so this one here, so you can also have an island that's only like a 1 by 1 island as well. But the important thing to catch here is that although there's like what you might call this island here, because it's on the edge, you actually don't consider it. So you only consider the ones that are completely surrounded by water on every edge, so they can't touch any of the corners. Okay, so it's it's a pretty popular question. Like there's a lot of ones like this, and so you follow kind of a general templated answer for a lot of these matrix graph problems. So let's go ahead and implement it. So because we're dealing with this matrix, we don't need an adjacency list or anything. So we can just go ahead and write out the code. We don't really need the only external data structure that we need is like a visited set, which just keeps track of the land points that we've already visited before, and we're saying, okay, we already visited this island or this particular part of the island, so naturally, let's not keep visiting it. So yeah, so otherwise, if you don't have this, you'll get like that TLE, because you'll just kind of keep recursively doing the same work. And so that would be like an infinite loop. So yeah, let's go ahead. And the first thing that we're going to do is we're just going to want to iterate through every cell in this matrix here. So for every row and for every column, we want to see, okay, did we find an island? Did we find a zero? So let's do that. So the first thing we want is the length of our rows and columns. Then let's iterate through all those rows and columns. Great, and so now that we've kind of iterated through every single row and column, we want to see, okay, did we find a closed island? And we want to return, like, or we want to add to our count whenever we see that. So naturally we need a count, and we expect to return this at the end for our program. So then we're going to say, okay, when do we want to add to our count? Well, naturally we want to add to our count whenever our kind of depth first search function that we're going to implement above returns true. And so that will represent, okay, we found a closed island. Now you could say, okay, why didn't I, like, instead of returning true, I guess you could kind of like return an integer or something, but with each iteration of the depth first search, how I thought of it, and I think most do in the solutions, is just, okay, you're just performing this depth first search for one instance for every island, because you just look for, okay, is it a zero? If so, let's go and traverse that island and see if it is completely enclosed. Okay, so if this returns true, then we want to add to our count. So we naturally want to pass in the index of where we're performing this depth first search. But we only want to do this depth first search if it's a zero. So if our grid at this row and at this column is actually like land. And then also the second thing we want to check is, okay, did we actually visit this before? So, and if our row and our column is not in our visited set. And this is kind of just templated code that you typically write when you're solving these two-dimensional grid graph problems. Great, and so that looks good. All right, and so naturally we want to pass in the row in the column here because we're performing the step for search at that index location. So the first thing that you want to do is say, okay, we want to make sure that we stay within bounds. So we don't want to accidentally cross out of the matrix here, and that will return an exception. And so we just say, okay, if our row is equal to -1, or our column is -1, because that naturally you're out of bounds. So we don't want to accidentally try to index into something that's out of bounds. And then, or if our, let's see here, or if we're also like, because right now we're checking -1, but you also want to check, okay, what if we're at the rows, like beyond the length of the rows, or beyond the length of the columns here on those edges? So we say, okay, if row is equal to rows, and this is like the length of our rows that we defined above here. And so next, we also want to check the columns one. And so in this case, you actually want to return false. And that's because naturally, or not naturally, is that, okay, say if we're at this index location, we will return false when we index out of bounds here, because any of the landmasses that are on the edges, you don't want to actually consider closed island. So if you're at this location and you index into here, let's just return false immediately, because we know that, okay, anything that's touching these out of bounds edges will be not considered a closed island. And so next, what we're going to do is we want to see, okay, we want to return true if it's a water block. And so, because one is water, and so if you index, say, at this location to the left, and then we see that, okay, that's a 1, that we want to return true. So if at our grid for this row in this particular column is 1, then we want to return true in that case. Okay, and so after this, let's say that the only way you can get past these cases is if it is actually like a land block. And so we want to continue on from here, and we want to say, okay, we've now visited this particular piece of land. And so we add the row and the column just to indicate, okay, at this particular row and at this column we visited it. And so now we want to go in every possible direction. So we want to go up, we want to go to the right, go down, and to the left. So at any particular grid, you're going to want to go in all like the 4 dimensions. And so we say, okay, there's the left, we want to go left, and that's equal to our depth first search at our current location, -1, or no, row, no, be this column, -1. And then if we want to go right, then we just go to the column next to it. And if we want to go up, then we just add to our column. And naturally, if we want to go down, we want to subtract. And so we only want to say that, okay, this island is completely enclosed if they all return true. And so if at every four directional way that you can go, they all return true and they aren't going out of bounds, then you know that, okay, this island is fully enclosed. So let's return true if left return true and right return true, and our upwards direction and our downwards direction did all return true. Okay, and so this looks pretty good. I think something's missing here. Let's just see. The other case that we want to consider is we're not actually checking this visited set within this depth first search function. And this can cause problems because, well, a lot of these are shaped like donuts. And so you can see here, let's just get out my pen. And so say we visited this one, and then we go downwards and we visited that, and then we visited this one, and so forth. We go like this. But because we only check our visited set in this function here, that's calling our depth first search function, while we're performing this depth first search function, we actually want to see if we visited a cell within this island before, because otherwise we'll end up, I'll get another color here, getting back to this cell, and then you're just kind of infinitely going around over and over again because we're not checking, okay, did we visit this before? And so we also want to say, okay, if we visited this, so otherwise if our current row and current column isn't visited, then we also want to return true because, well, we only set it to true if it's a landmass. We don't set it to true if it's water here because it only gets this point if it's land. And so as long as, okay, we visited this land before, then we can say, great, that's fine, return true, because we don't want to perform a depth first search on something we visited before. Oh, something's wrong here. Just move me up here. Yeah, I'm not sure actually what the is kind of method does there, but I actually did is not visit, but you naturally, I keep saying naturally, I have to stop saying that, is if this row and column is not in visit there. Okay, try submitting that, and great. That looks good. So yeah, that's the algorithm. It's pretty templated, like you'll see a lot of these matrix graph problems in LeetCode and everywhere. They're very popular. And typically, whenever you see them, you should think, okay, I'll have to iterate through every row and every column. Often you want to do depth first search. You can also do breadth first search, which works good if you're trying to find like the shortest path to something. It's very nice to have these rows and columns constants here so that it's easier to check when you go in and out of bounds. And then just setting things to true or setting things as visited or not is very important. Otherwise you have those cycles. And yeah, that's pretty much the template here. So yeah, I hope that helped, and good luck with the rest of your algorithms. Have a great day.